It is time for linear transformations. So as you can see from the picture, linear transformations are functions that take vectors little v from the domain, which is a vector space, to the codomain w, which is a vector space also. And linear transformations are functions that follow these two rules. We say that they preserve addition and scalar multiplication. What's of note here is that this addition is the addition defined in the vector space V, in the domain, that V, and this addition is the addition defined in the vector space W. Of course, scalar multiplication here is defined one way, and scalar multiplication here might be defined differently. So again, the operations inside the parentheses occur in the domain in V, and outside here, there are operations that occur in the codomain or in W. So let's see. Of course, I will have to show you again. Let's see how this works. We have an example where I'm going to show that a function that takes 3 coordinates, so it takes vectors from R3 into 2 coordinates, that makes it R2. For this, we have to find the image of V and the preimage of W. So of course, to find the image of V, we plug V in, and we have to do what? This is V1, V2, V3. We're going to mix them up in this way. So this says, just for notation, I'm going to write this as 2, -3, -1. So technically, you would need a set of parentheses because you're plugging stuff into T, and another set of parentheses because you want to indicate a vector V, but there's no real reason to have 2 sets of parentheses, so drop 1. So we just use 1 set of parentheses there instead. So now we're going to say 2 times V1, so that's 2 times 2, plus V2, that's -3. That's your first component. The second component is V1 minus V3, so that's 2 minus 3. So this transformation takes 2, -3, -1, 2, 1, and of course this is minus a negative, so it's 5. Now for the preimage of W, well, that could be a whole set. So the things that get mapped to W, the things in the domain that get mapped to W, could be a whole set. They don't have to be just one vector. So to find the preimage of W, we must find coordinates x, y, and z such that when you put these x, y, and z through the transformation, you end up with -1, 2. So you want to find all the possible triplets that get mapped to -1, 2. So to do that, we're going to say, all right, I'm going to put this through the transformation. So T of x, y, and z are going to equal 2x plus y, x minus y. So you see z is not involved. That means z can be anything it wants to be. So we're going to say this is equal -1, 2. And so we can form a system of equations. 2x plus y equals -1, and x minus y equals to 2. We've already reduced this. And we get a unique solution only for x and y though. So the unique solution that I worked out and I got is 1/3 and -5/3. What does that mean? This means that, so I was looking for 3 components. I found 2 of them. There is no mention of z. That means z is not involved. Z can be anything. So the pre-image of W is the set, the whole set of the form 1/3, -5/3, and a parameter t. And so this is a whole line of vectors not going through the origin that through the transformation gets sent to the one vector, -1, 2. Next, so if you look at problems 1, 3, 5, and 39, they're done in a similar way. Now, to show, there's 2 problems in your homework where you have to show that a transformation is a linear transformation, or a function is a linear transformation. For this, you have to pick 2 vectors. So we're going to let u and v be vectors in R3. Then we're going to have to add them. So we're going to call them u1, u2, u3 plus v1, v2, v3. We're going to add them first, and then we're going to put them through the transformation as given here. So once I've added them, I end up with u1 plus v1, u2 plus v2, u3 plus v3. Now I'm ready to put them through the linear transformation, and so I'm going to end up with u1 plus v1, right? u2 plus v2, and then the z component goes to 0. My goal is to split this into 2 vectors, so I'm going to go with u1, u2, 0, plus v1, v2, 0. We see that if we put the vector u through the linear transformation, that'll have the effect of creating a 0 here. So this is really t of u. This is t of v. Now, similarly, so we verified that the transformation preserves addition of vectors. So now we're going to let u be a vector in the vector space V and C be a scalar. Then we're going to have to first multiply the C through. Let's do that. So we end up with CU1, CU2, CU3, and then we're going to put CU through the transformation, so you get CU1, CU2, 0, which is the same as factoring out a C, U1, U2, 0, and so this equals C times the vector U. Now, because my function preserves addition and scalar multiplication, we say that T is a linear transformation. All right, so this is an example of a linear transformation that is defined by multiplication by a matrix. So the vectors u and v in M33 are going to be 3 by 3 matrices. So we can call u vector B, matrix B, and v could be matrix C. So the way we showed this is first you want to add B and C, and then you put B and C through the transformation. There is no need to express this in any different way. So we're going to say, well, I know how matrix multiplication works. if I have left multiplication here as defined by the transformation, I will have to perform left multiplication here as well. And so this becomes 1, 0, 0, 0, 1, 0, 0, 0, negative 1 times vector b plus 1, 0, 0, 0, 1, 0, 0, 0, negative 1 times vector, well, matrix C. And so clearly this is the image of B, because if you put B through here, you get this matrix times B. So this is T of B plus this here is T of C. So we showed that the transformation preserves multiplication, left multiplication, the transformation preserves addition. We can do the same thing using properties of matrices when we want to multiply B by a scalar. And so we're going to first put this through the transformation, 1, 0, 0, 0, 1, 0, 0, 0, negative 1 times C times B. Properties of matrices allow us to move the C out. And now you see that this here is the image of B under the transformation, so it's C times T of B.